Okay, I think we can start this this webinar. So I hope everyone can hear me loud and clear. I am Giacomo Mezzetti from INTIA Florence, and I work in the MARE project. We deal with dissemination and communication of the project. And today, it's a big pleasure to be here and host this webinar as a moderator. So we have an event very much rich in content. We have 4 speakers, and I will start very briefly to introduce them to you. The first speaker is Henrik Schlosser from Air Liquide, Germany, and he's project coordinator. Good morning, Henrik. Then we have Michael Bampu from Center for Research and Technology, Hellas, and Chemical Process and Energy Resources Institute from Greece. Then we're gonna have AJ Kushik Venkatanaramasi, sorry if I didn't pronounce it well, from the Delft University of Technology, the Netherlands. And then last but not least, Ismael Matino from Scuola Superiore Sant'Anna from Italy. So I think we can start with a presentation from Henrik, making a general overview of the MARE project. So Henrik, when you want, the floor is yours. Thank you.
Yeah, thank you very much, Giacomo. Also from my side, it's a pleasure to welcome all of you to our webinar today, where we will be talking about advancing the sustainable maritime fuels. And within the MARE project, we are looking at then the holistic value chain of the production of maritime methanol to decarbonize the shipping industry. And so we are looking at methanol in particular because it's one of the most promising alternative fuels in order to decrease greenhouse gas emissions within the maritime sector. So we see the maritime sector in the EU actually is responsible for a significant amount of greenhouse gas emissions. And so by switching to alternative fuels such as methanol, we can achieve significant greenhouse gas and CO2 emissions savings. And so actually what we see in the market right now that there's a big push and that methanol is emerging as one of the most promising alternative fuels. So there are more than 250 ships, container ships, currently in operation or on order that are capable of running on methanol. So typically these are dual fuel engines that can run either on methanol or on conventional diesel. And of course, the hope is that with the supply of renewable methanol increasing, that these ships will continue and increase their time running on renewable methanol. And so what we are looking now in the EU-funded MARE project is to produce a new low-cost, low-carbon methanol process that is able to, from biogenic CO2 and renewable hydrogen, produce this maritime methanol in order to meet the ambitious targets of decarbonization set out by the shipping industry, by the ship owners and the IMO. So we are really looking at the whole value chain. So starting from the renewable hydrogen production via electrolysis, looking at the biogenic CO2 sources. So where are they available? What are the limitations of each of the different CO2 sources? And how can we use them in order to combine it with the hydrogen to produce the renewable methanol? And so then in the next step on the pilot scale, here at Air Liquide Innovation Campus Frankfurt, we demonstrate then the synthesis from CO2 and hydrogen into methanol for several thousand hours under different operating conditions. But we are not stopping there, so we go one step further and try to improve the existing process with a new reactor concept in order to save capex and be more flexible in the operation of the methanol plant. Next, we are also looking at the purification of the crude methanol that comes out of the synthesis. So we need to remove the water that is formed during the reaction. And there we propose and test a simplified purification in order to make tailor-made maritime fuels. But to test these new fuel grades, we and our project partner Everlands does a lot of testing on their engine equipment and injection systems, looking at the performance and the lifetime of these equipments in order to validate the methanol that is produced within the project. And very crucially for this project is to look at the whole value chain and to, first of all, analyze what is there and then to optimize. And this is also what we are looking at today. So the project started in December 2023 and will run for 1 more year. So we have plenty of results to show you. We are very happy to also, if you have any questions, please feel free to put them in the chat, and we are happy to answer all of your questions. And so with that, I would like to hand over the word to Michael for the first presentation.
Thank you, Eric. Thank you very much. Yeah, something I forgot to mention at the beginning for the attendees. So first of all, thank you very much because you are many, but one thing to manage, so you will have the Q&A box to submit the questions. So our speakers will be able to answer live on the Q&A box, or if we don't have like enough time, we will submit them to the speakers by the end of the sessions. So we will have a specific session to submit the questions. And then for any other communication, so if you have like any sound problem, image problem, so you can submit them in the chat box. But I think we can continue with Michael. So whenever you are ready.
Thanks a lot, Giacomo, and thanks a lot, Henrik. So let me just share my screen. I hope you can see it in.
Perfect. Yeah.
Okay, thank you very much. So this first presentation is about providing an overview on the complete value chain in order for you to also understand better the process and also the challenges that such a bio-CO2 to methanol, to maritime methanol value chain faces, and also provide a path forward towards scale up, towards further research, and also in order to see across the value chain several challenges that might face. So starting first with an overview, here you can see the different processes that are involved throughout the maritime methanol value chain. First, we'll start with the bio-CO2 sourcing and the supply of bio-CO2 feedstock. Namely, we're going to see about the complexity of the different bio-CO2 emissions, the condition requirements, also the impurities contained, some capture processes, and also the storage and the transportation considerations of CO2. Then also very important is the supply of green hydrogen. So we're going to provide a very brief overview on green hydrogen production, what are the challenges of connecting different renewable energy sources and electricity, and also some storage and transportation requirements. Then we're going towards the production of methanol, and we're going to see how to produce methanol and what are different grades, and also the distillation, the simplified distillation that I will hand over to Henrik to provide more information. And finally, we're going towards the port and provide some indications regarding the different scales for utilizing methanol in ports, and also an overview of feedstock demands and the transportation requirements. So starting first with the bio-CO2 supply. So bio-CO2 sector is a complex sector in terms of volumes of upstream processes, composition, impurities, and also emissions per plant. So in that case, we started by categorizing the different bio-CO2 emission sectors by low volume and high volume, which are the pulp and paper industry, biomass combustion, and also the biogas sector, and also regarding high purity and low volume, which are the bioethanol sector, food and beverage, and biomethane. So those sectors differ in terms of total CO2 emissions. The CO2 concentration in the stream, for example, combustion-related processes, which are mainly referring to pulp and paper and biomass combustion, are diluted in terms of CO2 concentration, contain a lot of nitrogen and also NOx and SOx emissions. Seasonality aspects are also very important. For example, when biomass combustion is connected to a district heating plant, this means that the CO2 emissions will be higher towards the winter season where heating is required. Also, current uses of bio-CO2 are very important. For example, in the food and beverage industry, since CO2 is very pure, it is also used internally. Other bio-CO2 emission points within the plant, for example, in biogas plants, there are different points within the plant where you can recover the CO2, for example, before the cleaning or after the cleaning or after the combustion of biogas or biomethane. Geographical distribution and the emissions per plant are very important also for the logistics, since larger plants concentrated emissions, which is mainly the case for fossil plants, but also for pulp and paper and biomass combustion units, could enable economies of scale also for producing methanol in economical matter. So also very important is the potential impurities or other compounds that might be included within the stream. And this is also very important since it depends also on the biomass feedstock and on the upstream process before producing before emitting the CO2. In that case, regarding the impurities, what we did is we performed within the project 4 sampling campaigns at 2 biogas plants and 1 biomethane plant and the 1 biomass combustion plant. We also employed a CO2 capture unit using membrane gas absorption using a DEA mixture in order to offer a compact and relatively novel technology for carbon capture also for smaller scales. We evaluated the impurities across all the stages before, during, and after capture of that CO2. So we performed the sampling of those for plants and analyzed the solutions using standard analytical protocols, and also included the regeneration step to recover the high purity CO2. So what we found is that in biogas campaigns, after capture, the residual chlorides were higher than the catalyst tolerance limit for that particular sampling day and period. And also very important was that the NOx levels for the combustion flue gas were also increased, so it might indicate that you would need some pre-capture conditioning before applying the capture technology. And also what we also showed was that approximately 99% of those contained impurities were removed using the MGA unit, and the purity was 99.9 volume percent of the CO2. Now, going forward, after capturing the CO2, we would need to store it in order to account from the difference in between the production and the usage of CO2. CO2 can be stored in a liquid or gaseous form, which will also differ in terms of the pressures and the temperatures that you would need for both forms. In terms of gaseous, there are also compression requirements to compress the gas until the storage pressure. And for the liquid form, you will need there are lower volumes required, but you will need specialized equipment. In terms of transportation of the CO2, since in many cases methanol synthesis will not be done where the CO2 is also emitted, there you will need also to transport the bio-CO2 in the synthesis site. So this could be done with pipelines at dense or supercritical form. So you would need also compressors and booster stations to account for the CO2 and the pressure drop. And also this could, for lower volumes and short distances, trucks and rails are also employed at liquid form. And for ships, so for large scale and long distance transportation, we also see that there is CO2, liquid CO2 ships, CO2 carriers currently ongoing and under investigation. Going towards the green hydrogen supply, green hydrogen is also a very restricting component in terms of the overall value chain viability. Green hydrogen can be produced with water electrolysis using renewable electricity, such as solar, wind, hydro, geothermal. The purity is be up to 99, minimum 99.9%, and also the efficiency could range depending also on the electrolyzer technology that is employed. In that case, the electricity price is the main cost driver for producing hydrogen, and also afterwards will be also the main driver for producing competitive methanol. So if you can produce hydrogen, renewable hydrogen at a very competitive cost, this will be very beneficial for producing competitive methanol. Also regarding the electricity supply and the operation strategy of the electrolyzer, electrolyzers can be connected with renewable energy sources directly, which can lead to lower capacity factors overall. They can also be connected to the grid via, for example, certain agreements like power purchase agreement. You can achieve higher capacity factors, but they are subjected to grid and market constraints. Green hydrogen can be stored as compressed gas, which is also widely used and can lead to a certain energy penalty depending from the energy content of hydrogen, depending also on the storage pressure. Liquid hydrogen is also an option, but the liquefaction process is also very energy intensive. There are also some other forms of for storing hydrogen, cryocompressed, but they might require are at a lower TRL level and have a higher complexity compared to the other two options. Also, hydrogen can be transported via a pipeline and can be cost effective for large volumes and distances. Also, an option might be repurposing natural gas pipelines, and for short to medium distances at smaller volumes, trucks and rails are also an option to transport hydrogen when it is not produced on site. Now, going towards the methanol production process, here. Conventional methanol synthesis process includes a reactor, high and low pressure flash separation of the products, and a recycled stream in order to achieve higher conversion rates due to the thermodynamic limitations of the process. And finally, you can purify the product to achieve a grade that might be suitable for the engine that the methanol will be used. So you can remove the dissolved gases and the water to produce methanol that might be of MMA or MMB grade or MMC grade that contains higher water. So what we also investigate in this project is the multi-reactor integration. So in this case, after producing methanol in the first reactor, there are the liquid products separated through a flash, where in that way you can push the reaction towards towards the products again, so you can achieve higher methanol synthesis product amounts without even requiring a recycling stream, which can slow the dynamics of the process. And if there are high inert contents, but also lead to accumulations of those components. It also would require larger volumes of the different components. So such a multi-reactor scheme can has the flexibility of handling different streams, can lead to increased feedstock conversion to methanol, so reducing also the feature requirements, and you can minimize or fully avoid the recycling stream depending on the feedstock that you will handle. Now regarding the methanol purification, I hand over to Henrik.
Yes, so in order to test this new simplified crude methanol distillation, we built actually a pilot plant that is directly connected to the existing methanol synthesis pilot plant. So the feed is up to 0.5 ton of crude methanol per day. And then we are able to produce these tailor-made maritime methanol grades. So as mentioned, either these MMA, MMB, or MMC grades, but also to go even higher with the water content. So first tests show up to 20% of water and higher. And all of the methanol that is then produced in this pilot plant is sent to the project partner Everlands for their engine tests. So within the frame of this research project, the goal is also to test different water contents, also higher than the current specifications allow. Because of course, if you purify your crude methanol less and have more water, it uses less operating costs. And also with this concept, we only need one distillation column instead of multiple ones, which are common in commercial large-scale processes. So we can also save on the CapEx side. And the first 1,000 hours of testing showed very promising results, achieving a high efficiency and very flexible in the operation. Plus, with this new setup, we are mainly concerned, of course, about the water content, and the byproducts that are formed during the synthesis are not harmful for the combustion of the engines. So we are also investigating having more byproducts in the maritime methanol in order to actually increase the heating value of the fuel and thus increasing the efficiency of the whole value chain.
A lot, Henrik. Now continue with methanol storage and transportation. So a very important advantage of methanol is that it is liquid under ambient conditions. So it has easier handling than, for example, gaseous fuels like hydrogen. And you can use the existing infrastructure with some modifications, less modifications than, for example, for gaseous fuels. So it can be stored in ambient temperature and pressure with above ground floating roof tanks. And methanol can be the most dominant method to transport methanol is through shipping and ocean transport, which is mainly due to the utilization of methanol widely in the chemical industry. For smaller inland volumes, small to medium volumes, and short distances, rail and road tankers can be also employed. Methanol pipelines are mainly used within terminals or chemical industrial sites. There are also mainly 3 different bunkering methods in order to provide methanol in the ship that will use the methanol as fuel. For example, truck to ship has a lower investment and is more flexible, has lower volumes and flow rates. Ship-to-ship has higher volumes and fast transfer, but also has high capital cost. And terminal-to-ship is high capacity and can provide fast bunkering rates. The location is fixed and has lower flexibility. Now, finally, going towards the analysis of the ports, what we did is we mapped the different bio-CO2 sources based on what we also showed in the first slide, the total sector emissions, the emissions per country, seasonality, current uses, and we also mapped them accordingly in the different EU countries. The same we did also for green hydrogen, where is current green hydrogen capacity located, some targets based on the short-term targets, the medium-term targets for hydrogen production. And also we identified some indicative starting points and in order to use the methanol in ports, which we also consider the port readiness of and also the activities that are currently undergoing in the different ports regarding renewable fuels and renewable energy projects. What we did is the first two indicative cases we considered Rotterdam and Antwerp, the two ports, in order to see how the different volumes of feedstock would what the capacities of the different feedstock would be, in order to see how we can efficiently supply them, and if they are according to the targets, for example, for green hydrogen. Starting from bio-CO2, for three different starting points for replacement of the fuels, for example, 0.5, 1%, and 2%, you can see that the single source supply, for example, starting from the 0.5 to 2% of the bio-CO2, this would be feasible for very large scale plants like biomass or pulp and paper facilities. But for smaller scale emitters like biogas plants, other actions should be undertaken, like clustering of the CO2 to achieve the higher capacities required for that replacement. Regarding green hydrogen and electrolyzer size demands, as you can see, could range from 140 to 800 megawatt, and based on future regional targets, this could be met if the targets from the European Union and the different countries are set, are on track. Regarding the methanol, what we saw also is that depending also on the different scales of current methanol synthesis plants, these are within the range that are currently commercially applied. And there some challenge would be regarding the capital investment, the operational costs, and the feedstock sourcing, which is the two main restricting factors in that case. Finally, what is also very important is about since methanol synthesis will most probably will not take place directly at the ports, so there will be large volumes needed to be transported to the ports from the production locations, and the storage demands will be also depend on the time frames that you would need the methanol to be stored there. So shorter time frames will increase the reliance on the frequent deliveries, whereas longer horizons will provide greater supply security and resilience, but will require more space and more storage capacities. And this currently there are several terminals in the port of Rotterdam equipped with handling for handling methanol, and the same is also for Antwerp Bridge port. And also regarding the transportation of methanol, for example, through trucks or rails, and the truck transportation will require the highest number of trips due to also the lower volumes of methanol will be can be transported. The main outcome here is that the ports need to have an extensive inland and connection also to the methanol synthesis hubs, and be positioned to accommodate the methanol supply. Now, just as an overview, we did here was a first techno-economic analysis, a case study for the biomass combustion plant that we also performed the sampling campaigns that we showed in the first slides. And we can see that the electricity, depending on the different electricity price on the left side, you can see how it can affect the final methanol product. And on the right side, you can see how those methanol production costs relate to the current methanol price, the average gray methanol bunkering price at the port of Rotterdam. And you can see that green hydrogen cost and CO2 feedstock cost are the main components that can affect the competitiveness of methanol production for maritime purposes. Now, the final slide, some recommendations and the roadmap to support integration and scale up. As we saw also in the previous slides, for small scale emitters of bio-CO2 like biogas plants, bio-CO2 clusters and hubs could support the integration and scale up, since they are typically small scale and geographically dispersed. And hydrogen valleys that are also under development across the European Union. Hydrogen valleys are a complete hydrogen ecosystem from production until end use. We can also use in the future cheap hydrogen that can also be used for the production of methanol. Efficient methanol synthesis schemes, what we also saw in the previous slides, and that can handle also different kinds of feedstock, will provide the flexibility and the resilience for the process and can reduce the feedstock requirements. Dual fuel engines that can also be used also conventional fuels like diesel, can also be a short to medium term solution for until methanol synthesis will become competitive and available in the ports across Europe. And also very important are maritime regulations, since the maritime sector is very conservative in terms of change. They can help close the cost gap and also enable scale up in the future. That was it from my side. Thank you very much, and I'm really looking forward for your questions.
Okay, thank you very much, Michael. Thank you. I mean, this was really exhaustive. You covered like all the aspects of the value chain, so it was super. So we have a question actually, so we can submit it now. It's from Taras Lenyuk. Hello, Taras. So the question is related to the methanol synthesis section. So maybe for Henrik. So what type of reactor have you tested for single and multi-reactor integration schemes, and why?
So currently we have tested tubular reactors, both for the single and multi-stage concepts. And we are currently working on also pillow plate reactors, which offer better heat transfer and lower production costs. So this is what we're currently installing in the existing pilot plant to be able to compare the different reactor concepts with one another.
Okay, thank you very much, Henrik. So I will have just one from my side very, very quickly. So during the tests that you conducted, was there like any particular challenge or engineering barrier that you encountered? I mean, if not, you can say no. It's not mandatory, but it was a
of
very
course,
generic
I mean,
question.
there are a lot of challenges always when you build such a plant. For us, one of the main challenges is that as a research, we want to test as many operating conditions as possible. So our design parameters typically cover a wide range. And so within the design, we need to make sure that we can operate at all different conditions safely and reliably.
Yeah, I see. Okay, thank you very much. So for the moment, I think we can switch to the next presentation from Ajay. So whenever you're ready, Ajay, you can share your screen and start presenting. So the floor is yours.
Thank you, Giacomo. I hope my screen is visible.
Everything fine.
All right, thank you. So, thank you, Michael, for the presentation. I think you set the platform for what I'm going to talk about now. It's on strategic design, logistics, and production planning. So I'll present this with Ismail, who will talk more on the production planning side, and I'll be talking on the design part of it. So it's kind of the same thing, but with a bit of data. We looked into 9 different countries in the European Union, and we mapped every single plant in the sectors which Michael discussed, all the way from combustion to waste incineration, pulp and paper. What we see is 2 different patterns. So what this graph tells you is the size of the circles you see. It tells how many plants are there, and the color intensity tells you what is the amount of CO2 you get from it. And you see it's always on the other ends. If the plant number of plants are smaller, then it's always a darker color, and it's the other way around. For the larger circles, you have lighter colors. So what does it mean? Is these sectors have a lot of CO2 that is available, but the concentration at which the CO2 is available is low. That's why the cost of capture is going to be higher in these sectors. On the other end of the spectrum, we have the sectors where you have a lot of CO2 plants, but the net availability is less. And so here, the cost is going to be low because it's already available in a purer form, but the net availability is low. So this is just the status quo based on actual plant data that is collected from these sources. Moving forward, the total availability in these countries altogether is 143 million tons per annum, and which roughly translates to a methanol potential of 99 million tons per annum, which of course assume the fact that all the CO2 is going to methanol. So this is the potential availability of methanol. Now moving to the demand side of it, we see we looked into 5 different ports in around this region, and with Rotterdam being the leading demand center, and also Antwerp, and 3 other smaller ports in the different regions around the chosen countries. And they have a net demand today, as of today, as 23 million tons per annum. This is the amount of conventional fuel needed. So methanol equivalent will be roughly 2 times of it based on the energy density difference. And on the right side, you see what is the amount of methanol that would be required at different demand growth rates. And we found it to be, so on the last slide, we saw 99 million tons of potential is there, and all the numbers you see on the slide are less than 99, which means theoretically we have enough CO2 to completely satisfy this demand, but only again under the constraint that all the CO2 is given to us for methanol production, which might not be the case. But this is to put together things in a context, how much we need and how much is available. So now I told when I was discussing the slide on the circles, we mapped every single plant in these sectors in the 9 countries chosen, and this is the exact geographic locations of these plants. And you see some chemical symbols here, which are possible hubs where methanol can be produced. This is based on some GIS technique. We tried to find out some hubs closer to the plants. And the red ship symbols are the 5 ports that we chose for the supply side of it. Now, looking into it, what we can infer is biogenic CO2 sources are unevenly distributed. Around France, we have a lot of biomethane plants. Around the Nordics, we have a lot of pulp and paper. So the sources are unevenly distributed. And the ports which we are interested in are geographically at a distance from these ports. They are not co-located, right? So this brings us to two different sets of problems. The first one is a techno-economic layer, which Michael talked about in his slide on the cost of capture and methanol production and all that. So because the CO2 is available in different concentrations, quantities, and different kind of impurities available with them, the costs of CO2 capture is going to be different. Also, the methanol production can cost differently based on how big the plant is, because a larger plant would lead to a lower per ton or per unit methanol cost. So yeah, so that is one part of it. The second part is the spatial or infrastructure design, where you have to take a call on, if you are proceeding with this, where to locate methanol production. Do we do it with the plant which has CO2? Do it near the hydrogen production? Do we do it at the port? And if we do it at a different location, what do we transport? Do we transport CO2? Do we transport hydrogen, or do we transport methanol? And if we choose to do them, what do we do? Pipeline, truck, train, various different options are available. So this is the second layer of the problem. And in today's talk, I'm going to mostly focus on the techno-economic layer. Here are, like I said, because 5 different sectors, all different characteristics because of size, because of impurities, because of the concentration of CO2 available. So we looked into all the plants and we said, okay, there could be the size range. For example, if you take biogas, there is a size range based on the available plants. Same with biomethane, same with all the sectors. So we chose 2 points on each sector, and we developed detailed models to estimate the cost of all the sectors. And just like how they were distributed in the very first plot, you can see these 3, which were the dark red ones with smaller circles, is costing you more, around 100 euros per ton of carbon dioxide. And these 2 on the other side, which were larger circle with lighter colors, they are having a bit of a lower cost. And this one was not shown in the first graph because it's too expensive and there are too many plants. We don't expect this to play a major role as compared to these things. But of course, we expect at later point of time, if needed, it will be. There is also a reason which I will discuss a bit later in presentation. But for now, these are the costs. Going to methanol, like I said, based on the scale at which we produce methanol, we can get lower prices as the scale increases, as you see here. But because hydrogen being a very big chunk of this cost, the reduction in capex is not really visible here. So that's one of the results, important results. And also we took 4 euros per kg, which probably is an optimistic cost for hydrogen. And this is how the methanol stands. Putting them all together, this plot, I'll try to take you through what it means. The sectors, as I discussed from all over this presentation, let's imagine every sector is producing methanol from the CO2 of its own. So they will have a different methanol cost, which is what you see on the y-axis. And these colored blocks here, the green, the dark green, blue, and all these different represent different sectors. So for instance, if you take biomass combustion here, it means it costs around 1,120 euros per ton of methanol if you produce methanol from this this sector. And it can produce so much of methanol based on the availability in 10 countries. And the vertical lines you see here, these are the demands in different growth rates and different times of different times. So what it means is, I'm sorry. So what it means is the red block you see here, the biogas, may not be necessary even under a high demand case, or unless CO2 is rigorously allocated to some other thing other than methanol, then we are good with these three sectors, which are the combustion based, where the availability is quite large, and also it can satisfy the demand. Finally, a quick introduction on something called as learning curves, which we are developing a methodology right now. So technologies learn with time. So when there is more electrolyzers, more compressors, more CO2 compressors, then we learn them, which means there will be a reduction in cost, lower capital cost, and the efficiency of these things will improve. So, for example, an electrolyzer can consume less electricity per kilogram of hydrogen, so the hydrogen costs will go down with time. And also, when there is more deployment of methanol plants, the average size of methanol plants will go down, which also means there will be a reduction in cost. So accounting for all this, we developed a methodology to see how, under a severely optimistic condition, how low can the cost of methanol go. And here, it's based on the announced projects for e-methanol so far. It's 64 times more than the current capacity, and the prices can go as low as 720 euros per kg. But this is a very optimistic number. But this is just to show you that the prices can go down. And with this, I would hand over to Ismail to continue his talk on production planning. Thank you for your attention.
Thank you, Ajay. Hi, please.
Ismail, sorry,
yes,
just
please.
a second, because we have one question in the chat box.
Perfect.
I don't know. Maybe you already answered, Ajay, but yeah, let's try to explore it. So it's from Said Bentuba, and he asked the cost of energy consumed to produce 1 ton of methanol, and which technology is used.
Yeah, I think it's a very generic question in some sense, because energy could mean a lot of things. But when you look into the cost perspective, if you take out hydrogen, then the energy itself is very less. It's less than 5% of the total cost, because the cost of CO2 and hydrogen are the major drivers, like I showed. And which technology used? It's thermochemical synthesis, which has been widely explored. Yeah.
Yeah, that's it. Thank you very much, Ajay. So yeah, Ismail, please, if you want to continue with the presentation, you can share yours.
Okay, perfect. 1 second. Okay, do you see my screen?
Yes, perfect. Thank you.
Okay, perfect. So I will talk now of the second part of this presentation. So the part related to the production planning. That is one of the parts that we are studying in terms of optimization in this project. And with this slide, I want to highlight that this is not a mere exercise, an optional exercise, but it is something that is very strategic. Why? Because in the context of bio-CO2-based maritime methanol value chain, we have different challenges to be addressed. Some of them are here, the most important ones, the key ones are here listed. So first of all, we have to manage the volatility and uncertainty in feedstock pricing, but linking also with that, to provide flexibilities against fluctuation and variabilities in feedstock supply and also qualities of the feedstocks, as discussed and presented by Ajay, but also by Michael. Then we have to ensure dynamic efficiency in hydrogen production processes. Why? Because as you learn from previous slides and presentation by the colleagues, it is the primary cost driver of the whole value chain. And considering all of that, we have also to enable balanced decision making for both economic but also environmental sustainability. This point will be also clearer in the further slides when I will show you how we want to manage the two things, the economic and environmental aspects. Okay, going more in detail, we foreseen in our in our project to develop a tool that can allow to optimize the whole value chain on different levels, 3 levels. The first level is the logistic and transportation level. That is something strictly related to LCA and TIA. So that is more or less what presented by Ajay and by Michael to find the most promising location transportation options. Then we have the second level, that is the ones that I want to describe you more in detail in these slides. That is the planning, the second level of optimization, the planning optimization, and that is more or less in the medium short term horizon of optimization. Then we have the short-term time horizon that is more operational optimization and real-time optimization. So together, today I will talk of the planning optimization. So something related to weeks, months, so dedicated planning optimization mode. Going more in detail, the idea is to plan the purchase of feedstocks in an horizon of 2-4 weeks. Why this horizon? Because longer horizon is not trustable due to the prediction of cost and the uncertainties in cost. Then we want also to plan the production, considering also the expected demand of the maritime methanol. But for doing that, we have to include all the aspects that need to belong to the value chain. Obviously, in a simplified manner, because there are different, as I already said, the different uncertainties. We have also to fit with the optimization constraints in terms of computational burden and so on. So we have in some way to simplify some aspects, but we want to include all the aspects of the value chain. For instance, starting from the producer, so from the feedstock of bio-CO2, we are including in our optimizer models that allow to consider and predict availability and cost, the average composition, the addition and the cost and energy demand of additional treatments. These allow us to consider some penalization for some of these bio-CO2 feedstocks. As well as we will have some models, dynamic models, for considering the variation of the storage of these bio-CO2, as well as we have dedicated models for the part related to the hydrogen. Hydrogen that can be both purchased or also produced in site. And so in this case, we have also to consider storage. For the purchase, we developed advanced model based on machine learning and on artificial neural networks, specifically to deep ecostate neural network, for allowing us to predict sometimes ahead, some days ahead, the hydrogen price, as well as also renewable energy production. For hydrogen price, it is very important for the purchasing part. For the renewable energy production, is very important if we want to produce in an optimal way, so in terms of considering also the availability of the renewable sources, and so the possibility to produce green hydrogen. So this is very important for the production. Here you can see some graphs of these predictions comparing the real values that are the red ones with the predicted ones, that is the blue ones. And we are including also static models for different kind of electrolyzer that cover more or less the most important range of available electrolyzer in different range of technology readiness level. But we want to include both alkaline, PEM, as well as SOEC electrolyzer to assess the hydrogen production, the energy and water consumption, and the relative cost. We have then the part related to the synthesis plant. In this level of optimization, we consider static models that derive that are surrogate models, that are simplified models based on other two more complex ones that have been developed for other purposes in the project, as well as also we have the part related to static model for distillation. The dynamic model for considering the variation of the storage of the produced methanol. And then we have a final part related to the consideration and the optimization also of the effect of the methanol features of the methanol quality on the ship engine performance that are regression models based on test bench data. But going on the mathematical representation of the problem, before going on that, I want to give you also an overview of some assumptions that we included in our consideration. Okay, the horizon I already said. We consider a granularity of 1 day. We consider that markets that we know in some way with models or with other in other ways, also the cost and availability of feedstocks, as well as we assume that CO2 purchase that arrives in the same day. We know also the methanol cell contract. We included also some storage assumptions. So the capacity of the storage, that here there are only some examples, but could be adapted to the plant size. Again, as I already said, we include a static equation for the static model for methanol plant. We want to consider the cost of the distillation for achieving the specific qualities in terms, for instance, of water content in the methanol, the produced methanol. And again, also hydrogen, as I say, we want to describe with static models. Okay, going more in detail on the problem formulation, I want to show you some aspects that we consider that are very important for better understanding how the planning can be optimized and what are the most important parts. Starting from the most critical ones, so that is the hydrogen production. I say that this is very strategic, and if we want to produce hydrogen in site, we need to consider some aspect. And for doing that, we consider the possibility of binary modulate the active stacks of the electrolyzer according to the demand of hydrogen and according also on the available renewable energy. And to be more realistic, due to the fact that in the electrolyzer, the efficiency of the electrolyzer is not linear with respect to the operating power, we simplified again for respecting the constraints of the optimizer. We simplified with a piecewise interpolation the curves that correlate the efficiency in function of the power, in order to consider also this aspect. Then here you can see how we want to consider the variation of the availability of hydrogen when it is produced. So it is stored, and then we want to consider also the variation of the availability in time. Then there is the part related to the feedstocks. To the feedstock, where there are some constraints related. So we translated the one of the most important one is this one, that is the translation of some contracts in some constraints. And also we consider some maximum availability for the different sources in the function of the period, because some sources have a big seasonality to be considered. Again, there is also equation related to the storage. For reactors, I already said that for reactors, we consider some simplified aspects, such as the efficiency, the conversions, and the production in function of some operating condition, as well as of the characteristics of the feedstocks. And we consider also the aspect related to energies. And constraining also the part related to the water, because the water is the most critical aspect for the usage of methanol in maritime sector. Here, the storage part of the methanol, and then the part also related to the engine. How we are considering that? We are considering with an integrated penalty factor, here expressed as a function of the different aspects that affect the performance of the engine, that are the fuel consumption, the emission, the exhaust emission, and the crankcase emissions that are related strictly with safety, for instance. In order to simplify the problem, and in order to make it in function of only the water content inside the produced methanol, we assumed a load, an engine load, in that can be fixed in two ways, or in a worst case approach, so considering the load that provide the worst performance, or in a more realistic case, that is a duty cycle approach. So something that consider how the ship is generally managed during its operation. Obviously, it depends from the ship, but we can decide different loads, for instance. And here, the objective function that highlight what I said at the beginning. So we consider all these aspects that are related to cost and price, so that are related specifically to the economy of the economy of the value chain, but we consider also a factor that is based on LCA. So we include the LCA, some aspect of the LCAs, for instance, with a global factor derived from the LCA that allow better incorporating sustainable aspect in the problem. Okay. Concluding. From what presented by Ajay, he presented that the path to cost competitive in methanol, and that one of the key challenge is the allocation, since potential methanol availability exceeds maritime methanol, and the fact that, as I also repeated a lot of time, green hydrogen is the dominant driver of methanol cost. Then it is clear that also the high purity CO2 is limited in availability. So concerning the bio CO2 methanol production, based methanol production, this could be a very critical aspect. But if we consider in the whole methanol production, it is expected that the combustion-based sector are expected to be the primary contributor to the methanol synthesis, due to the fact that they provide higher content of CO2, but if you consider the bio CO2 part, also the combustion-based sectors are the ones that are, I can say, provide more stable availability and also more stable availability of this feedstock. Then components-based learning curves show costs that are expected to fall as low as 700 euros per ton of methanol. From the point of view of integrated optimization, I presented what we are working on related to the production planning optimization and the importance of having an holistic and integrated chain interdependence that we consider thanks to interconnected models that link all the different value chain components that are mutually influenced by upstream and downstream decisions, but also disturbances. What are disturbances in our cases? For instance, the feedstock and the markets. And then the fact that we have a dual benefit objective function that consider both economic profitability and environmental sustainability. Okay, so what we expect to do in the future? To have a spatial optimization, to complete the spatial optimization problem introduced in the strategic design analysis, to investigate also other competitive maritime fuels in order to make some comparison, to explore alternative routes for producing renewable methanol, and also to conduct a life cycle assessment for all the selected pathways in order, again, to complete the analysis of that. From the optimal management by CO2-based maritime methanol value chain, we have to finalize and implement a different optimizer level. After that, we expect to make some offline scenario analysis in order to both to check the tool, but also to provide some analysis. And everything will end with a proof of concept of the optimal control strategies. So in order to close the loop of the optimization. So that's all from my side, and every question is welcome.
Thank you. Thank you very much, Ismail. Could you please mute yourself, Ismail, because I hear myself. I don't know if it's that. Okay, thank you. I don't see any question in the Q&A box for the moment. I invite all the attendees to submit them, if any, or if not, it means you've been like very much exhaustive with your presentations as you did. So I just take the chance to say that I will share this in the chat box to say that you will find most of the resources that we are producing as press releases and publications and papers and fact sheets and whatever is related to the project itself and results on the link that I just shared. And our new newsletter, third issue of the newsletter, is just about to be released by the end of June, or at least at the latest for the beginning of July. So you will be more than welcome to read it. And also we are about to, I mean, not about to organize, but we are planning a new joint webinar by the end of the year, joint webinar with other EU projects that we have collaborated with in other occasions at other conferences. So no questions, I see, for the moment. So I think we can conclude this webinar like that. So I want to thank everyone, all the attendees, for being able to participate and for your attention until now. So it's more than 1 hour that we are connected. So thank you very much for your attention, and thank you to the speakers, to Henrik, to Michael, Ajay, and Ismail for your professional contribution to this webinar. It was really a pleasure to host it. And again, to the speaker, to the attendees, please just stay tuned because on social media and a LinkedIn page and on the website, you will be released updates soon in the next months to come. So thank you very much, and I hope you will enjoy your weekends. Thank you.
Thank you all.
Thank you.
Bye-bye.